was heading in for at this point. But I come back, you take Goodwin in the part he played, Foxy Grandpa-like.
Yeah, but he did the same thing. He gave these Sunday parties. He lived out here in Brookline, had a lovely house.
That's right.
And always got the faculty together once a month.
Great. It was an atmosphere that meant a lot to all of us, I'm sure.
Well, it was a different institute from that fashion, but the numbers have made a tremendous difference.
Yes, that's right.
That's right.
Well, my second major experience with Bush was indirect when I was in his wake at this point. Was being given the sheaf of his papers on the 37 and 38 memoranda on electronic digital computing, the first of their kind. I was given also later the responsibility for doing something with them by way of editing and readying them and putting them into report form, which never happened. But I still feel a responsibility to see that does happen. But then I joined the Center of Analysis, which he had caused to be formed, but then left before he could actually take a hand in its operations. Spent many years there all through the war. Left after the war and wound up in the RDB in 1948 while he was still there as a consequence of Louis de Flores proposing a formation of a committee in a certain activity by the RDB. And my last involvement with
Chairman of the Electronics Committee.
Yes. Yes.
I would like to say just another word. I'm as bad as my friend on the right here. But
Who's right?
I think we've talked about Van and Lawsey and the rest of this tribe. I always, by the way, think of the filter paper that came out, brilliant red, and it had a picture, Julius will remember this, a picture of two figures on the front. One was a walrus and the other Pop Laws. It said the figure on the right is Professor Laws. He had this wonderful mustache, and he looked like a walrus if you wanted to interpret it that way. But to come back, I think that it's worth bringing up the name of Gilman. Ernie Gilman was a great force, a great factor, and I think it's wrong to say unappreciated. And granted, if Ernie was left alone, there wouldn't be a man in the Institute who didn't take network theory. I mean, he was an addict and a devoted soul. But we come back, he and Weiner got along. He could understand Norbert, and Norbert would come in and talk to Ernie, and I haven't any doubt that Weiner helped Ernie a bit. And Ernie was a wonderful synthesizer. I'm not talking about network synthesis. I'm talking about the ability to get as much pleasure out of the contributions of others as he would out of his own if he had made them. So his books are a magnificent memorial, because in them there is consolidated, again, a sort of a house cleaning of all the work on network theory, network analysis, and network synthesis.
But I don't think he was ever given the credit.
That's it. It's a classical contribution.
Yeah.
Well, Ed, one thing we haven't mentioned, because it goes back to some of the criticisms of the professional work, but you certainly played a very key role. I always thought Dougal Jackson was running it, and I know that Bush was involved, but the curriculum revision program that led to the three blue books that started in 1930, in the mid-1930s, was, I think, the beginning of a renaissance around here. Gilman was very deeply involved in it.
That's right.
You were. I knew that all the way through. But I can cite an incident. I'm surprised how much Compton knew about it, because Compton actually helped finance my first return trip back to Australia by engaging me to make an ECPD inspection of the University of Hawaii, and at the same time to revise one of the chapters in one of the, eventually was revised later on, for which I got a $200 honorarium. But as I look back on it and now see what came out of that work, it was a very astounding revision in the whole substance of electrical engineering education.
Well,
And the,
I appreciate that, but it took a little bit of gall because it was like our modern politics today, or rather the Reagan situation as I see it. There was a lot of negativism. I mean by that we had settled down to a quiet, easygoing course, excepting for people like Harold and Gordon and the rest of you. It needed a jerking up, a springing together. And a loudspeaker, for instance, was never treated as a motor, as if you could think of it in electrical terms or in acoustical terms, and things of that sort. And we ended up, I think, stirring up the things a bit. And I believe it would have happened anyway, as most things do, if you leave them alone long enough. They kind of rectify themselves. But with the work of the small group, it was a great need to, I don't like to use the word revolution because it wasn't a revolution. And you bring me, Gordon, back, however, to a question that has always interested me, and I've never gotten very far as I meditated or thought about it. And that is, Jackson came here in 1907. And in my day, as I measure him, it was his belief in the young.
yeah.
Bush came into the department and lended a kind of scientific integrity, or whatever you want to call it. And that, as I see it, he was what I would call an engineering type. And we've been talking about computers and the like. He was analog-minded innately or somehow congenitally. And by the way, I don't believe it's realized, I have a book here just for the fun of it, that old Sammy Stratton, the President Stratton of the Institute, was himself a great analog man in his day.
Well, he came to of standards, didn't he? Which was an analog institution.
He worked with Michelson.
Sure, yeah.
And there's an
Before he came to Washington.
excellent piece in this book on the computer. It's written by, the title is From Pascal to Neumann.
Oh, I've got that, but I've got a different.
And Goldstein wrote this book, and it has a great bit on Stratton.
Does it? I didn't know that.
Yeah, I didn't know.
Yeah. This is the one.
I would
See, that's it.
Yes.
like to
There
comment
goes
a
the
little
big bag.
on great textbooks and their demise, more or less. And part of the trouble is the book publishers
Oh,
who want people to write anything, anytime, so they can sell more books. There are also people who feel some books are too hard. Now, Ned Frank wrote 2 wonderful books for 801 through 4.
Yeah.
This was in the 30s. I still refer to them today. They're concise, they're exact,
Very good.
accurate, and they have good problems. Everything you want in text. But a number of people said they're too hard to read. There aren't enough words, there aren't enough pictures. So Sears writes a book that isn't in the same class. It
Absolutely.
sold 1 million copies.
Right.
Yeah.
Practically owns his own publisher, Addison Wesley.
But I agree with you completely.
Now, there are 2 other sets. There's the University of California at Berkeley series on physics, which goes from freshman to senior, I guess. About 5 or 6 volumes, including Ed Purcell's book on E&M, which is a wonderful book. And somehow or another, these 2 have just sort of been lost.
Yeah.
And then the classic example, and a very amazing one, is Dick Feynman's 3 volumes on physics,
Yeah.
which he teaches
Another student of
freshmen
mine.
and sophomores at Caltech. They were written in a very peculiar way. Feynman would give a lecture. 5 professors, count them, would take notes. Then Matt Sands would take these notes and correlate them and write down what the lecture said, and that's how the book got made.
Is that right?
There were 3 volumes. Just wonderful. The problems were too hard for anybody, some even for Feynman. But they had easy problems too. And the style, you can, when I read it, I can hear Dick Feynman talking, and he's a wonderful speaker. But they're lost.
Well, I'll mention
maybe
another one,
Caltech.
Bedell and Crehor, we goes way back. And you begin to find, if you've looked that over, how many of the electrical engineering treatises of today have borrowed heavily from that classical text on which Cornell started to build its electrical work department.
Let me ask you this. You knew Bill Radford well.
I beg your pardon?
You knew Bill Radford well.
Yeah,
What did you know of his work on electronic digital calculating circuits at the behest of Bush?
He did some work for Bush, I know
Yeah.
that. At Round Hill, we ran out of money. And Bill was sort of free for a while, and Van took him on.
He started to work probably early in 1938.
Yeah, and I gave
Up on the third floor.
Up on the
yeah.
third floor.
I gave Carl, I have a copy of that Bill wrote, and I can't tell you what's in it, but it was a vacuum tube usage, vacuum tube application, and as I remember, digital.
Yes, that's correct. Yeah. I saw it
But
in the winter of
It was
38.
the decimal system that was involved mostly. Bill, he went a little further than that, but not much further.
That's right.
It was a kind of a charitable work on Van's part too, because Bill was looking for something to do. So I can't evaluate that contribution.
I knew Bill from 42 on to his death, but I never knew he was involved in computers.
Yes, he was.
Yes, he was.
A little over years, my
You know,
guess.
he was very interested in police communications.
That's right, he had as a
The
consultant for the
radar
state
school and
on that.
then Lincoln Lab.
but he'd been down at Round Hill.
Bill was a delightful soul, and he and Houghton made a wonderful team
Good.
on all this light penetration work and even the fog dissipation work.
Well, after Bowles and Houghton and Van de Graaff moved out of Round Hill, RLE took it over under
right.
Radford, and then Lincoln took
That's
it
right.
over.
That's right.
RLE.
Either way, I'll
Then
make
the
a,
Jesuits got it.
I want to make a side remark here, if I may, as long as we're chatting about sweet nothings, and sometimes these nothings may be bigger than nothing, but you can imagine such a consequence. The fog dissipation required dropping calcium chloride down, this is one embodiment of it, dropping calcium chloride solution down through a curtain with the idea that the drops would absorb the water vapor. And on the basis of that theory, at least, you now would assume that if you cut down the vapor pressure, the fog particles evaporate. And so they did. And then came the problem of not wasting, because if you had the drops of calcium chloride too big, they fell down and didn't do their job. If they had them too small, you made a fog. So there was this delicate interim. So a piece of work was done down there that is, I believe, has made a little bit of history behind the scenes, and that was a study of how to produce drops, get a distribution that had a maximum without the lobes being too large, so as to conserve liquid, because you had to use barrels of it and spray it. So you had to make a nozzle that would give you the smallest particle size that was needed here, not too large, not too small. And with all that work, papers were published on it by both Houghton and Radford, as I remember it. And it never occurred to me that, although I had done trapping as a youngster out in the foothills of Ozarks, that we had more to learn from the skunk than we ever had to learn from a lot of the computations that had been made.
How to keep away from them.
And they had, what we found, or Houghton found, we had two opposing nozzles. And the stream collided, and you got a fan, and with a certain adjustment of space and so on, you got a maximum distribution of the size you wanted. And the old skunk, God bless him, has the same system. But we didn't have enough sense to.
I think they used that in powder metallurgy.
Well, that's true, probably.
I'd like to get back to Bill Radford's project.
I'd like to ask a question on that. I'm glad you said that. Bill Radford, I think the paper you're referring to is sitting right there. Maybe
That's
if you
correct.
saw it, it might jog your memory. Radford wrote a document that is a precursor of what was built at the University of Pennsylvania. Not exactly.
I beg your pardon?
but very close. Radford's document describes various ways of making an electronic computer that is similar to what ENIAC finally built. Not exactly, but there are things close to it. And he talks about different number systems. Now, you just made a remark that's fascinating. He said he was looking for something to do. Could this have been just, I mean, Bush gave him a pile of memoranda and they talked about something and he came up with all this and then went on to something else completely? Or did the project end because of the NCR case? Or is there something else?
Because of the the Rapid Selector program?
Well, no, this is the Radford arithmetic circuit project. Well, it didn't end really. Radford apparently wanted to get back to something closer to his tube interests. Bill Overbeck took the project over on the electronic side. And I joined the project at the same time Bill did, working on magnetic recording. But were you familiar with Overbeck's work?
Just I knew him, but I didn't know much about it.
He was the first one to build multi-megacycle counters.
This is Bill Overbeck or Radford?
Bill Overbeck,
Overbeck.
carrying on after Radford's period.
Right.
And by 1941, he had multi-megacycle counters running. And then turned his attention largely to specialized gas tubes.
Yes,
that
he did some work on that.
counting
Worked for
functions.
Raytheon, I believe, on some of it.
Well, he worked at Raytheon earlier and joined MIT from Raytheon.
That's right, that's right. Wasn't that when the problem of the storage tube came up?
No, Bill never worked on storage tubes.
He didn't.
He didn't. Well, not storage tube in the later sense. He built what he called a sticotron, which would have a thyratron type beam stepping around along between 10 spaces between plates. But Bill wouldn't have worked on storage tubes. He had no faith in them.
He was right.
But Bill did turn out excellent reports. Bill Radford turned out an excellent report here, and Bill Overbeck turned out excellent reports too.
He did a thesis for me, and it was an exemplary kind of thing.
Overbeck did?
Yeah.
Oh,
Radford.
Oh, Radford.
Tell you an interesting story about storage tubes. Poor Forrester went into management. He was head of the computer group at Lincoln Lab, and he brought the whole whirlwind project with him. And it was in that period, or perhaps just before, that he got the concept of the magnetic core storage device and built it, made it work, and so on, and invented ways to build it. It was a beautiful thing. The patent argument that began later was fallacious on the part of the people who objected, but we finally won. But when we put this computer, which was to be the heart of the SAGE system, out for bid, there was no way of evaluating it on money. We could only evaluate it on what the company said it would do and things we knew about the company and how close it was and so on. We went to 10 companies. 4 dropped out immediately. 1, Bell Labs, dropped out about 6 months later, leaving 5. And their proposals took about 6 months of building, and when they came in, IBM was clearly the best. In all respects, it wasn't even close. And IBM lived up to all their promises and so on. Well, George Valley, who's of a suspicious state of mind anyway, said, IBM really didn't want that goddamn computer. They wanted the storage device. They wanted to get Forrester's storage device before anybody else. And I was inclined to agree with him, but it was about that time that I left Lincoln. I found out several years later that after IBM got the project, they went back to the storage tube.
You mean the whirlwind storage
system.
tube?
Yeah.
Good Lord.
However, it took us 2 years to talk them out of it. We finally forced them out of it. And then they did a magnificent job with the cores. But they weren't after the cores at all. They were after the computer. And they understood the storage tube. They didn't understand how lousy it was, but they understood it.
When was that?
This is 56, 57, we're in there.
Golly, I find that hard to believe.
I know, but this is,
Well, when
That's
I
it's
one
been
of the big-
sworn to me by guys who were involved. We gave them the contract from Lincoln in mid-53. That lasted about a year, and then that was $1 million, which is nothing. And then the Air Force gave them a $100 million contract or something that led to that.
That was
And
the
it was in
time
that period.
of the terrible argument. The MIT,
Search Corporation.
the Project Mac.
Yeah. Well, Project Mac was later.
No, it was about 55 that started. And it did finish up in 66, I guess you're right. But the first beginning of the trouble, I think.
Talking about
Well, the Project Mac didn't come along
No, that
until
didn't come along.
1960.
No, you're right about that. Yeah.
Talking about troubles with companies with whom relations aren't always good, I'd like to get the story of the National Cash Register conflict clarified. Go ahead.
Well, I can tell you a little about that. I can't tell you the whole details. But first of all, Reichman at RCA, who had seen Forrester's work, went back home and immediately wrote up a patent proposal. And somehow or another, he got a patent, although Forrester's had been in there first. But he changed a word or two and got a patent. And there was a 5 or 6 year fight, I think, before it was settled. And this is R.J. Horn's great contribution to humanity of winning that case.
RCA, was it?
Yeah, Reichman of RCA.
Yes.
And we won it. And we settled with IBM, as I recall, for a flat fee of like $10 million.
13.
Which was peanuts. We should have gotten 3 times as much. And we settled with all the other companies on a bit basis. All except one, and that was NCR. And NCR just refused to pay. And then sometime in the 70s, because I had become vice president for research by then, NCR sued MIT, IBM, and somebody else, perhaps Bell Labs, I'm not certain, but 3 organizations, under the antitrust laws. So I got hold of an excellent antitrust lawyer at, our law firm. And he said, well, let me tell you, antitrust law is the craziest law on earth. And you can't really take anything for granted. You have to fight each case not only on its merits, but on the feeling of the judge and the jury and whoever else that day. And he said, your case is very clear, but this doesn't mean you're going to win. He did an excellent job, but he was a bit unstable personally and actually wound up killing himself. Now, I had been assigned this task by Howard Johnson because they wanted to keep the president's office out of it. Jerry and I both felt that since we had charged everybody else, we shouldn't let NCR off the hook. And we should not settle with them for nothing just because they were bringing a suit, though we could have done it. Johnson got hold of the great trial lawyer at the 2-name firm, the biggest firm in Boston, has just 2 names. Oh, hell.
Wasn't Fisher Richardson
No.
and Fisher Richardson and Lee?
No, this is not a patent firm.
Oh, I beg your pardon.
This is a regular firm. They have 100 or more partners. It doesn't matter. They had a very great trial lawyer, and Johnson knew him. So he just, without talking to me, just hired him and replaced my man, who later killed himself, not because of that, but as I say, he had personal problems. And I Belt Johnson had taken over the case from me and he could have it. But I still was a good soldier and attended hearings and the like. And this man was all sweetness and light and logic and so on, and the NCR lawyers were a bunch of tough meanies. And, we finally settled out of court for nothing. We didn't pay them anything, but they didn't pay us anything, and I think that was a boner, but I can't quarrel with it. It was done.
Did NCR's earlier support of work for Bill Radford and Overbeck and for me come up in any way?
Not that I know of. See, this was all on the core memory
Yes.
per se. And this was the non-linear, hysterical magnetic core which went on and off and strung wires through it.
Yes.
Well, as far as we can tell, there was an earlier case that had nothing to do with this, which is you just referred to. Was that, something happened with NCR and Radford's work, and that got MIT involved? I don't know how far they went in terms of legal problems, but eventually, what, pulled out?
No. Well, when Overbeck left and I went off into other work, there was no more work going on at MIT to be supported by National Cash. But were you aware that Van did go to Colonel Leeds and get support from National Cash for that work?
I may have been, I don't know.
Colonel Leeds was the chairman of the
When was
board
that
of
work
National
done?
Cash at that time. Beg pardon?
When was that work done?
Well, Radford did his work mostly in 1938,
Yeah. But see, this was
much later.
15 years later.
Yeah.
But it was in the 50s or?
No, 38, it's in the 30s.
Yeah, but the case.
Well, the case that Al was just talking about was the core case,
Yeah.
which was in the 50s, mid-50s.
See, after all, Aiken had a digital computer long before that. So this was not on digital computers at all. It was only on the memory.
Yes, I understand.
And how you put it together. It was a pretty good patent. Well written and so on.
Let me inquire about the rapid selector and its conversion into cryptanalysis. Were you familiar with what was happening there?
Not in detail, no. Let's see, was Howard on that one?
John Howard? Yes, he was the senior
Yeah,
man on
And
the
there was
project.
somebody else,
John Coombs and Larry Steinhardt.
yeah.
Larry Steinhardt, that's it.
Now, I don't know whether Larry Steiner's still living, but the other two aren't, are they?
No, they're not. I was told that Larry was, told that fairly recently. I'd like to track him down.
And then there was a secret so-called communication system Ben was interested in, and he had a fellow by the name of McDonald who took some graduate work here, working on that, and I've forgotten the other man's name.
Well, that's the name I've been trying to remember. McDonald was up there on the third floor.
Is that right?
Yeah.
Everybody was on the third.
No, McDonald had an office back where I had one where Claude Shannon, and I knew that McDonald was working for Bush on this.
When would that have been?
That was in just about the time I was beginning to get involved in the servo work.
Bush
So
talks about
37?
Later than 37. Yeah.
Later.
Yeah, that I became aware of. Now, McDonald lived out in Concord.
Well, he was out in Wellesley in my day, right across the street from us.
Tall,
Great, big, tall
very
fellow,
tall,
yes.
big fella. Yeah, yeah. And,
Oh, wait a minute. What's his first name?
Waldron.
Waldron, yeah, I knew him.
I only remember McDonald, and I've been struggling for the
Very
last few
quiet
days to
guy.
think of
I
his
had him in
name.
class once upon a time, that's how I happen to know him, and he's a good friend.
I knew
He
him.
married well, and
Track him down. You'll
daughter
learn
of
something, Barry.
the best of Coolidge, Best and Rugg.
Oh.
But you never knew technically what he was about.
Well, that was a secure operation.
That was a secure operation.
Well, he
Yeah.
was also making department store inventory machines with magnetic drums and
Oh,
things
was
like
he?
that.
And McDonald went to Washington with this too, and it's mentioned in pieces of the
Yeah,
action.
the
pieces of
trouble
action.
there is that I think I can safely say this. The NSA and their Russian counterparts had very superior and complex encrypting machines in the early 50s. And that type of thing still is used, I think.
Well, what were the relations between these people who were working on that and the rest of the electrical engineering community? From what I hear, there was such a thick wall that ideas didn't spread, technical ideas. Would that be correct?
You asking me?
Any of you?
Anybody?
Well, I can only say that I knew Coombs, Howard, when they were younger. They were up there. I was with them. You'll find John Howard's photograph with me as some of the first photographs of the finished cinematograph. He was the senior assistant on that program. Then, as I said before, all of a sudden I began to sense that he was being drawn away by Bush. And all I knew was it was Bush and Coombs who were going in this area, and MacDonald. Mm-hmm. And it was, to me, it was not surprising that it was a secret project. It was not surprising that it was coming from Bush. I had formed, as you do instinctively, a feeling for the enormous number of things that Bush was getting involved in. And it seemed quite logical.
Well, I was aware of the project,
Yeah.
but obviously on the basis of security, forewarned security, I didn't pry, and MacDonald was a very good friend. I know that he was tight on it. By the way, we're talking about Forrester, and it may be in order to make to add a sentence or two. I was supposed to help Howard Johnson at one time in trying to spend Mr. Sloan's money. I'm exaggerating. But in the School of Industrial Management, and knowing nothing about management, I can only brag about knowing others who know infinitely less. But the problem was data handling or information processing, and it seemed to me that that was a missing element in that old school where they had bookkeepers or called accountants. I don't mean to be too harsh. And that the electrical department had 25 years or so of background in dealing with automatic computation of one kind or another. And along with Eli Shapiro, who was then on the staff, and I believe he's back on the staff now, we decided to do a little grafting. That's G-R-A-F-T. So it seemed logical to take Forrester and move him over to the School of Industrial Management. So I went to see Jim Killian, and Jim fell for the idea. I thought it was not a bad one. And that's what moved Forrester over into that environment, and it was kind of a breath of fresh air. It was a rash thing to do, but in a kind of a revolutionary move. And I think it's the beginning of a school of another sort. I mean by that Forrester is bound to get somewhere, it seems to me, with his talent. Give the school an aura that it wouldn't have had if you just left it in the hands of accountants.
Bookkeepers.
Now, Jay spoke of that twice, the assistance that you and Eli Shapiro gave.
Eli Shapiro, he mentioned that yesterday twice, yeah.
Well, Eli was no accountant by nature.
But very
He was a
valuable.
nice guy.
But he was not a no accountant, if I may put it the other way. He went with one of the insurance companies for a while, and then returned to the Institute, I believe.
I picked up off Eli's desk once a little sheet, 8.5 by 11, and it goes on the following. On every crossway on the road that leads to the future, each venturesome spirit is opposed by 1,000 bodies, all appointed to guard the past.
Very good.
Well, I'm writing a book, Gordon, and one of my chapter headings is The Age of Accountants. And I think we're in it. See, accountants have an easy job. They have 2 columns of figures, and they add them up, keep adding, and when finally they come out equal at the bottom, they're through. That's it. That's God's word. And I can't tolerate this myself.
Double entry bookkeeping, huh?
I don't care. What they call it, stink.
Bottom line, that's got,
The bottom line.
that's it, the vernacular of today.
Well, Ed, get on another one before you depart. Al, too. When were you aware of the stirrings in the domain of solid-state physics around here? By the time I was head of the department, it was sufficiently active so that it was one of the topics that I got considerable support from to begin to find a way to teach something like that in the course 6. And we used the term molecular engineering because we had von Hippel.
That's right.
But
My feeling is the EE department does as much solid state physics as the physics department. A different approach, perhaps.
Well,
do it.
and they were doing it almost, as I look back now, from the time von Hippel appeared.
Yep.
And he was very instrumental,
But
even
I
on the whirlwind magnetic core work. He helped Forrester on
I
that.
think the transistor was the key.
Yes.
Pushed you that way, that far.
Well, now, was that a Bell Labs emphasis,
Well,
or
this
did it
is-
come from Slater?
I should tell you the story about why Radiation Lab didn't invent the transistor. And the answer is very simple. The Japanese surrendered too soon. Because we had the transistor in our lap.
Well, that's
And
true
then
of
the
other
people who were working on it all wanted to go off and do something else. And Ed Purcell took Bob Pounds and, won a Nobel Prize in electromagnetic resonance, nuclear resonance. But the British reinstituted the crystal of Stratton's memory, and they did it not by having a cat's whisker you poke around, but they welded, or essentially firmly fixed a cat's whisker in a sensitive spot, then sealed the device, and got something that had a much better noise factor, and not too
As a
bad
detector.
a loss factor. Yes, as a detector only.
What was that for? Radar?
Bob Pound, Gerald Zacharias realized that the approach was all wrong, that what you should do is build the purest silicon you could, and germanium too perhaps, and then add impurities rather than go searching over different piles of silicon from different manufacturers and see which one worked better. And this worked fine, and GE picked it up and others, Bell Labs. And we made some excellent crystals with noise factors like 3 dB and amplification losses like 4 dB. There's a minimum of 3 dB because you throw away one sideband. And then Bob Pounds, we used to have a committee that reported on technical achievements every week, and I went in one week and said Pounds had a crystal down to 9 decibels, and I went in the next week and said it was now down to 6.5 decibels. I went in the next week and I said something is very wrong. It's now down to 5.5 decibels, so that's too low, or down to 3, I guess. That's too low. So this, I think, was germanium. Bob did a very hard study of it and found out that the crystal was oscillating at the intermediate frequency, and hence it was giving out a signal that hadn't been put in. It was generating its own. So we were fooling ourselves, and however, we made some good crystals out of it. At this point, Jerry, Zach, myself, a number of others said, why in the hell don't we put another whisker in there and see if we can't use it as a grid type of element and make an honest-to-God triode. And we were just about to do that when the war ended. Now, give Slater and Shockley credit for the wafer-type transistor. We would never have done that. That was pure Shockley, although Shockley gives a lot of credit to what he learned from Slater. I don't think Slater had a damn thing to do with the transistor. That was Shockley. And the 3-element transistor would have been very useful and so on, but it would not have revolutionized the industry. It wouldn't have led to these wafers with 1 million amplifiers in them or anything of that sort. But the invention was, as far as I'm concerned, damn near joint, except for the accident of the war. But the making it into an honest-to-God and important device is Shockley and Bell Labs. You just have to give them credit.
Well, Slater trained Herman Stotz, I know, and is one of the great disciples right after the Shockley period.
Well, Shockley was here from about 32 to 36, I think.
Yes,
Got
that's
a
right.
degree under Slater. I came just after
Slater rated
that.
this fellow Stotz another Shockley, and he's very, very brilliant soul. He's out of Raytheon. Well, he's published a good deal, and
Well, Perry, as you seek for little clues as to what happened to some of these people later on, I think from my point of view, you're bringing up this question of what's the half-life of the life of a laboratory? And my feeling is that there's a point that I would like to make. It comes to mind because after the war, I saw the radiation laboratory, which was very large, break apart because it had recruited from a lot of places and there were demand for the people.
It had no job.
And it had no job. On the other hand, what was created in its place was the research lab of electronics, which became in here and moved into the academic part of the system.
Yes.
Now, we're familiar with that. And what I look upon there as the key to its viability was the continual throughput of young minds. They'd come in, they'd stay for 3, 5 or more years, and then they'd go out. And I'll remind you that it would be worth your while to go back and look through the BBC programs of about 20 years ago, and there's a speech by Sir Alan Cottrell. He's now Sir Alan Cottrell. It's called Orchestrated or Syncopated, or words to that effect. I remember it very vividly. And he says laboratories have a very severe tendency to live for about 10 years after they're first created, and then they atrophy for some strange reason.
They do.
Now, he didn't supply the reason. I had, about that time, inherited in the EE department the problems of, for example, the acoustics lab, which was once very, very viable and active, but Beranek and Bolt began to become more interested outside. There was not the input of students, and I said to myself, there's the answer. It's the viability of these laboratories. It depends upon the throughput of students. Now, let me go one more minute. After the war, Tom Sherwood called me over one day and said, Gordon, when are you going to close down the Seville lab? He said, we've closed down RLE. And I said, when are you going to close down Draper's lab? To which I got no answer.
So you closed down RLE?
I mean radiation lab. I said, Tom, I think that what I see here is the Seville lab is very viable. It's got a guaranteed, ensure throughput of students. It's dealing with open-ended topics. It had the term servomechanisms laboratory. It was really feedback control systems on the broad front. So it was open-ended in that it didn't develop a device and then run out of business. Now, I think this is important for people to keep in mind. It was protected in many ways the same way Draper was protected. The students were coming in. It was a fertile ground for theses, and that to me is something that needs to be kept fresh before us, because today we need that more than ever. And I think many industrial establishments suffer because they don't have this natural way of turning over and keeping the viability going.
And the question that's really behind your answer is, what's going to happen to the Draper Laboratory?
Yeah.
Well, now,
That's what I wanted to address.
now, yeah.
Now, first of all, I think I agree with everything you said.
I do.
Just perfectly. I got connected with the Draper Lab January of 1970, I guess.
Yeah, about 70, yeah.
And then it became independent July 1st, 73. Initially, I was chairman of the board and chief executive officer because I was an officer of MIT. When we went independent, I insisted, and for good reason, that the president be the chief executive officer, and I remain as chairman of the board. I didn't insist on that latter, that was a suggestion. And this has worked fine, but about a year ago, I set up the retirement rules, because we didn't have any, and we finally decided, there we were, the directors all over 65, we better make some rules. And we extended a couple of people like Stratton and Sprague a year and a half.
Right.
We gave Fiore, Chick Hayward, and Hill an additional 2 years to keep some continuity. And then we made everybody else retire at 70 or at the annual meeting following their 70th birthday. Now this is bringing new blood into the board. But in my whole period with Draper Lab, I kept pounding on the officers, what are you going to do next? Well, they really didn't come up with very many good ideas. All kinds of, make-do ideas, get a little work here and a little work there. And this was silly because a $50,000 a year contract is about as hard to manage as a $5 million a year contract. So it was just an overhead begetting device. I said, and still say, that if we would concentrate on making an inexpensive gyroscope, an accelerometer, of about the same quality as the military ones, we could stick them in every airplane that flies, every major airplane, and we could solve the near airport traffic control problem, because we could take data from the instruments and feed it into a computer and get the men out of the loop in the control tower. But you can't do it with radar information, it's not good enough, so we still need the men. But you have to make it less expensive. Now, when the carousel and other commercial guidance systems came out, they cost about $100,000. And they're good. And the pilots love them because it frees them from the ground and they don't have to fly this way and that way over radio checkpoints. They love it, but it's not good enough for when you get near home. The average one, I'm sure you can fly from here to Los Angeles on autopilot and get within 2 miles, which is damn good. But it's not good enough for the final problem. So I think that is one thing we ought to work on, how to make it less expensive. And generally, things you make for the military have a habit of becoming less expensive because more get made. The military bears the brunt of the development, and you don't have mil specs to follow. You have specifications which are good enough. But I still think it might be 10 or 20 years off. In the meantime, we've made our mark by improving the instruments stepwise. Every year they get a little better. But you know perfectly well that's going to run out.
It's going to run out, right.
Strength of materials, unless somebody improves the strength of materials, it's going to run out. As it is now, I think Bill Denhart once told me that from data he had, he could tell where the center of mass of the spinning wheel was to within a fraction of an angstrom unit. Well, you know, that's pretty damn accurate. But we're not going to beat it much more. But one of the real troubles is that the officers and the department heads and so on are all very comfortable with the system under which they're living.
That's it,
They're
right?
doing good work, they're comfortable, they make a hell of an impact on education, make no mistake of that. And don't think we don't love it, because we get our best employees from the Institute people who have been through there. And all of this is important, but the life is not forever on these things. We have to do something else.
Okay.
I tell this to Duffy and the others, and they all agree with me, but then they go back to their comfortable situation. And that's called human nature. And I'm not damning Duffy and company, because I'm sure in their position I'd be doing the same thing. Now, there's one other thing we might do. We know how to do it technically, but not from a managerial standpoint. We have a multi-faceted control system that's really fail-safe. It increases decreases the failure rate to say 1 every 50 hours to 1 every 50 years or so. And we have things that no damn well we could control nuclear reactors with. We would not flood the floors of the reactor manned by old-line stationary engineers with pieces of paper, computer printouts and so on. This would all be done, and the operator would get something to read that he could understand. This can be done, but we have to convince, one, the AEC or whatever it's called now, we have to convince the utilities, we have to convince the manufacturers. And this is no easy job. We got one utility convinced, at least one division, we got support from them. But then another division said, hell, we can do that better for less money, that went down the drain. So until we learn, and I've given this speech ad nauseum, until we learn how to deal with the government, with the utilities, and with the manufacturers all at once, and convince them of the necessity of this, we're not going to be in the nuclear power business. Now, this does not solve the nuclear waste disposal problem. That's something else, but that's soluble, I'm sure. We've just not looked at it the right way. But if you look at how nuclear reactors are built, it's shameful and shocking. And I'll tell you one story, that Brookhaven reactor, Zach was on their board, and he took a look at it when it was building. And just by sort of a feel and a rule of thumb and so on, he said it's structurally too weak. He got Mac Hubbard, who's a first-rate engineer, to come down and look at it. And Mac made very careful measurements in about a month's study and said it's way too weak, and he could prove it. And who was manufacturing it? Babcock and Wilcox, who have gotten us in trouble since on other ones. Now, that is part of the problem. The controls, which I mentioned, which we could help with, and then just the business of making a nuclear reactor the same way you make a good airplane. Making sure everything is exactly right.
Right.
You cannot shave corners on anything. And that's not Draper's job. I mean, we're not experts in that field. But the Babcocks, the Wilcoxes, the Westinghouses and so on have not learned this yet. Or they're not willing to, and I don't know why.
Yeah, well, it seems to me the sinister aspect of all this, and I like to believe it's a commonplace, that you need a national emergency before you get the blowtorch on your tail and do anything. What was done during the war was done under emergency conditions. We pulled together our forces, even taking care of indigent professors like you.
I was a fired instructor at that time. I hadn't achieved the high rank of indigent professor. I agree with you, sir.
My point is that it's unfortunate, but it does take a damn near a national emergency. You'll never shake Reagan out of his optimistic position by just waiting and waiting and waiting for something to happen. Unfortunately, in our situation with Russia and with Israelis, waving a hand isn't going to solve the problem.
Don't say that too loud, because I'm scared to death. A war might start.
Yes.
And it's a war I don't want to see.
No, but my point is that it's unfortunate, but nevertheless, the great contributions come many times in the face of misery.
The things that have come out of wars, technically, have been tremendous.
Yeah,
What
you
kind of
were
an
saying-
airplane would you fly in?
You were
if we
saying
hadn't
this
had
a
World War
while
I?
ago, really.
Yeah.
The work that was achieved during the war was an astounding thing and a lesson to us all, and yet we don't profit by our lessons.
No, that's right. But I'd like to follow up on 2 points that have been made by Al and supported in a way by remarks made some of you others. Al, in your opening remarks this morning, you spoke about science and engineering. When you speak of science, you would count that as including engineering. Well, that's 180 degrees away from my doctorate. And it ties in with what you said about Babcock and Wilcox. And what you've seen there is simply not good engineering. And when I say engineering and science are completely distinct, I'm saying that the cardinal principle of engineering is the works must work.
Right.
And the cardinal principle that was correlated to that is that if you want to know whether they're working or not, you must have a performance spec. And you
Get
must
the
meet that spec.
accountants out of the act who are running costs on every goddamn piece of equipment the engineers specify.
Well, that's another issue, but what happened in World War II, and this, by my reckoning, and what is yet to be recognized is this, that engineering as we knew it in the old days, and by the old days I mean the days of building waterworks at work and electric supply works at work and a few others, the old engineering was upstaged by science in World War II, particularly by the physicists. There was a physicist, Zacharias, who engineered the weapons of World War II, not the handbook engineers. And after World War II, the departments of engineering in the universities and the institutes, well, the Department of Engineering in the universities became departments of engineering and applied science. And I have encountered deans of engineering and applied science who will equate engineering and applied
Engineering is applied science.
science. Except that applied science does not focus on the issue of the works
I
working.
will agree with you if you will change your wording to say applied mathematics.
I won't do that either. Engineering means to create, and you're creating works needed by man, and
Yeah.
works that work, that are safe, economical, and
Well, I
perform.
know, but look, here's one of the troubles. Take the E department here. It's probably the best in the country or the world. Isn't it?
Delete probably.
Well, I'm sorry. Okay. I was giving you an opening. I like to play straight man. They have changed dramatically since I first came here. And now you find many of them working on solid state physics or on computer science. And these are wonderful things. And they're things that are very attractive, and bright guys go and work on them. But somehow, we don't have enough people left looking after the structures. Now, the trouble with the structural engineering is that while people will spend $1 million extra to make fancy electronic gadgets to go into something, they'll shave on the dollars that go into the building, into the structure, and so on. And Charlie Miller applied computational methods to structural engineering, I believe, and was very successful at it. But again, there's always that opportunity for the cost accountants to shave there, because this really isn't important. The transistor will save us all, and the transistor won't save us all. It's got to be hard-headed engineering right from the start on everything. And we're losing some of that. But the question that you asked earlier was what's the half-life of a laboratory? And there aren't many that beat 10 years.
No.
Draper had. Lincoln has not. Lincoln is entirely different.
Well, the servo lab's entirely different too, you see. And this is why I brought in the concept of open-ended.
Open-ended
Draper's
is
still
all right.
involved with the gyro.
But here's the trouble with the Lincoln lab.
Yeah.
It's become a general-purpose electronics lab for the military.
Yeah.
And it's not super necessary to the military. The Draper lab is still super necessary.
But there's another thing about the Draper Laboratory. I mean, future existence. The Draper Laboratory came into being and was built around and was developed because of one man,
Right,
Stark Draper.
right.
Stark Draper is reaching his end. And when he's gone, the laboratory will go on, but will it be the same?
It can be, Jay.
It can be, but will it?
I tell you, I fight it every day. If I could answer, of course, to that, I wouldn't be fighting. But I argue with the people over there as much as they will allow me, because I'm scared to death it won't be. Now, the passing of Draper will make no difference, because essentially Draper is out of it.
Well, yeah.
He comes to all the meetings and he puts in a day's work every day. It's an amazing guy. But his influence is nil at this point, really. A little, but not very much. Now, his respect, the respect people hold him in is great, don't get me wrong. They don't talk down to him. They listen. But that adds another dimension to the problem.
It does.
But I still think the Draper Lab can survive if it starts solving the right problems beginning now. Now, it spends about $5 or $6 million a year, about half of it direct from the government and about half of it from their fee, their own money, on new devices and so on. But I don't think that program has been managed as well as it should be. I don't think it would have been as well managed as it should be if I'd been the manager either. So, you know, it's hard. It's a hell of a job. How do you point this now? And so I'm scared about this because, as you know, I've come to love the Draper Lab. And I don't want to see it pass along with the IDAs and the Lincolns, and the servos, which passed in a different way. I want to see it stay there as a top flight, high accuracy laboratory, but get the customers of the future lined up, and you got to line them up 10 years in advance. And it's hard to do when your own customer, who is giving you $100 million a year, says, do this, do that, change this, go help RCA, they got trouble with the satellite. We pulled a hell of a lot of other people's satellites out of the sky and got them straightened out.
Well, what seems to me that what we're getting into here is a problem that is applicable equally to the industry. It's generally what sprouts
Yes.
as a result of good management, and generally they'll call it a nucleus of some brilliant minds or a brilliant mind.
And industries seem to have a longer half-life, but
You have the thing in industry.
the thing in industry is